Okay, vertical stretch, eh? You threw me for a bit of a loop this morning when you asked that question. My mind, it gets so deeply involved in what I'm doing sometimes I don't change feet very quickly. But I was right. It has to do with, when I taught it, we called it compression or expansion. And if you look up quadratic functions dilations on the internet, you'll find scads of information. So I've set my little gizmo here to the quadratic function in its most sort of standard form or most simple form, where y equals x squared. And that means that the term that we're most interested in is a. That's the one that's going to be responsible for the stretch or shrink. And in case you're working with polynomial form, I'll show it to you here because a is the only term that the kids really have to look at to find out the factor of compression or expansion. If you've worked with standard form at all with your kids, you'll know that what they're calling h moves the parabola left and right. Another word for move could be slide. Sometimes you'll hear the term dilate. When I taught it, this term was lettered P. K, on the other hand, moves it or translates the parabola up and down, but you'll see that we haven't actually changed the shape of the parabola. H and K, or P and Q, as I learned it, just move the parabola around the grid. The only thing that the kids might have difficulty with, although they don't seem to have too much difficulty remembering, that if it's x plus, it moves to the left, and if it's x minus, it seems to be moving it to the right. Like they seem to be able to remember that they have to flip that over. But the simplest thing to do is to remind them that the formula is actually y equals a times x minus whatever letter squared plus whatever letter. So this is always a minus. The thing is that when the parabola is on the right of the y-axis, it's x minus positive number, and when it's on the left of the y-axis, it's x minus a negative number, which is why it shows up as a plus. So let me move the parabola back to its simplest location, or its simplest form. Oh, sometimes it's hard to get it right on the zero. Oops. I wish I could type it in, but I can't. Okay, so there we are. With the vertex at 0, 0, and the first kind of nice intersection point here, like if I can click on it here. So the first nice intersection point right there at 1, 1, and over here at negative 1, 1. All right? And that is the sort of the simplest form of the parabola. Now, I'm going to take you back to slope for a minute. And slope on a straight line graph for a minute, because that's where I actually start off with when I want to talk to kids about compression and expansion of parabolas. And these gizmos are kind of fun because you can actually get the kids to see what happens to the graph if they slide it up and down. And it's so much easier to see what's going on than it is on their graphing calculators if they're using graphing calculators. So here we are, y equals mx plus b. The slope is equal to 1. For some reason, they're not giving me a 1.0 here. It would be nice if they did. And again, the graph passes through the origin, and it has its first point, its first kind of nice point is right there at 1, 1. Which means that, of course, the run is 1 and the rise is 1. Now, this gizmo only gives decimal values for x, which actually works quite nicely, because so you're never going to see a slope of something like 3 over 2. I wish I could actually write on this board, but I can't. It's always going to be something over 1. And it's nice to show them that as they reduce the slope, so it's now 0.6 over 1, so the run is 1, and the rise is 0.6, that it makes the line more shallow. And as they increase the slope to, now let's double it, that we've kept the run constant, and we've increased the slope by doubling it to 2, right, which makes for what we call a steeper slope. And we can triple it from its original position, y equals x. So we're always kind of keeping that y equals x as our sort of baseline position, or sort of the simplest position. Let's take it up to 3. Again, oops, my aim's off tonight. There we go. Okay, so over 1, up 3, all fairly standard stuff. Now that's not a bad. What we're going to have on the parabola is something very close, but we can't really refer to slope on a parabola because this is a curve. It's not a straight line, but it's still a very simple idea, and a very similar sort of idea, just translated from straight lines into curves. So get your kids to think of the parabola a little bit like an elastic band, where they put one finger on the vertex and another finger up here somewhere where the elastic band kind of comes together. And if they hold this point fixed and pull, they'll compress the parabola, they'll bring the parabola arms together and stretch or expand the parabola upwards. And if they push down on the elastic band, they will open up the arms and flatten the parabola out. All right? So let's see what happens if we double the value of a. Now if that was x squared was not there, and this was a straight line, we would be doubling the slope. Now we're just going to double the a and see what happens. We're actually going to take it to 2 and see what happens. And you can see we've kept the run constant. You can't really talk about rise and run, but it's like keeping the run constant and doubling the rise. It has the same kind of an effect. We don't really talk about steepness. Instead, they say this is now stretched by a factor of 2. It's stretched vertically, because if this thing was, you can actually stretch horizontally, but they don't deal with that for a while. And by a factor of 3 with a run of 1 and a rise of 3, or by a factor of 4 with a run of 1 and a rise of 4. And if, go back through, oops, okay, if we take it to a fractional value, you can see that I'm flattening it and opening up the arms. So now we've kept our run at 1, and our rise is only 0.2, so that we've compressed the parabola by a factor of 0.2. You may be using the word shrink. And what happens if we take it to 0? It's totally flat, so that there is no parabola anymore. 0, 0, 0. That kind of makes sense. Well, what happens if we make it negative? Well, it flips and shows up on the opposite side. Now, the only thing that's important for them to remember about the vertical stretch, I'm going to take this to its simplest form in the flip version. So there we are at -1 equals x squared. So the parabola passes through right there, 1, -1, and -1, -1. So we know that we just took that very baseline parabola that passed through 1, 1, and 1, -1, and flipped her over. Is that when you talk about compression and expansion on the negative side, you don't use the negative term. So this would be vertically compressed by a factor of 2.6. The negative has a different role. The negative is not part of the actual compression or expansion of the parabola. It's flipping it over. So just remind your kids that if they're talking about vertical stretch with a parabola that's inverted, that they don't use the negative term when they're describing how much the expansion or compression factor is. And in 10 minutes, that's basically all there is to know about vertical stretch. I hope it helped.